Okay, let's start the. So, hello everyone. Let's start the session then. I'm Sai Venkatrakrishnan, a PhD scholar in the Department of Computer Science and Engineering at IIT Madras. So, this is week 7 live session for the course Blockchain and its applications. So if you have any queries in the lectures up till now, um, um, you can either unmute yourself and ask, or you can post it in the chat box and we can discuss those questions. So my plan for today's session is some of you have asked about in the forum. The main questions that you have asked is about PBFT algorithm, the consensus protocol, how it works. So I'll be discussing about mainly this PBFT protocol. So I'll just be explaining this protocol again. But before that, so this would be my main agenda, explaining PBFT protocol. And if time permits, I'll be touching upon one-way payment channels in Bitcoin network. So this is something not taught in your course, but I just wanted to touch upon it. Okay. So this would be the agenda, the broad agenda for today. But before I start with these two, if you have any specific doubts, I will discuss those first, and then I'll move on to these. So, any doubts?
uh, yeah, if we can get some more examples of smart contract other than like transactions based, uh, uh, like probably which is not there in the topic. Any other uh, applications of smart contract?
Smart contract is it Ethereum? Is it?
Yeah, it is the auto executed, right? Having maintaining it is a transaction driven. So, like in your understandings, so like other than any transaction based, any use case where you can use, you can just correlate with some use case and give some examples.
Okay. I came across so any other use case other than transaction. So this is not with respect to Ethereum, but one use case which I read long back with respect to Bitcoin. So Bitcoin also has the sort of contract code execution, right? Your that stack-based logic, that UTXO script, right? So in Bitcoin, in um, using the Bitcoin, what do they call that? The transaction script, the transaction script thing, script, the Bitcoin script code, right? So using this, what they have done is one application is for um, safe updates to software, secure updates. Okay, so the use case is, say you have your you have like a set of nodes running, say node 1 and node 2 and node 3, and this is all part of one single organization, say some organization. Okay, and they are using some software called they are using like a GPay software or something, and now instead of GPay, let's like assume some organization software. Okay, like we pay something like that. Okay. And now say this the owner of this organization, this software, this application is like, let's give it like name A1. Okay. And now say you have to update your software. A1 is rolling out a patch to this software we pay some security patch or something, and now if it should be like um, say some the attacker in between. Okay, so say your attacker comes in between, and what he does is he, he does some attack in such a way that instead of your the patch from the actual company coming and getting updated in each of these nodes, this doesn't occur. Instead, the attacker comes in between and he is able to fool your organization, and uh, thus and he makes you believe in such a way that whatever the attacker is giving you, that patch, right, that is indeed the correct patch which you have to update to your application. And if this happens, right, what happens is the attacker gets full control of your application, and each of the node is compromised. Okay, it is something like sort of a supply chain attack in software, as in you so in your if you are using Linux systems or Microsoft the Windows system, so like, or even in Google Google the Android platform, so your supply chain, so any application you install or anything, right, if you click on update, all the applications should get updated properly, and so the source from which it gets the patches and all those things should also be trustworthy, and it is easily possible for the attacker to fool you and make you believe that you are downloading a proper update, but in reality it will be some other malicious update which will corrupt your existing application, and it will give the attacker full control over your system. Okay, so to avoid this, one way is like you should use proper cryptographic primitives and all those things. This paper, I don't remember the paper's name correctly, so if I remember, it's called Katana. Okay, so what they do is they use the Bitcoin network. How they use the Bitcoin network is your say this organization A1, right? They will be having its own identity, like the public key and private key identity on the Bitcoin network. If they want to roll out an update to the software we pay means, they can create a transaction on the Bitcoin network, and if in the transaction, what they will do is um, the OP return part of that transaction. So any transaction, it will have an input field. So this will be your input and this will be your output, right? And the output will be the amount. The output will be like the amount which is to be sent to the destination, and the script. So this script is specifically as the conditions to spend this amount, conditions to spend. And if you remember, in Bitcoin, the script is actually stack based. Okay, and in a stack based script, there are many opcodes like OP push, OP pop, uh, and one of these opcodes, out of these opcodes, one opcode is called OP return. Okay, and this OP return is sort of like it just stops execution and does nothing. So in the script, if you take a normal transaction script, like say Alice wants to pay to Bob, right, the script this specific script would contain a set of instructions, like you should calculate the hash, you should verify the signature, and all those opcodes should be there. But instead, what Katana does is it will take the hash. Say your application vpay has to be updated by some 10 lines of code or something, the application has to be updated, so it will take the hash of that code which has to be updated, hash of that patch. Okay, and this hash it will place it as part of the script. It will place this as part of the script, and now your transaction, how it will look is, your script will actually just contain only one opcode, which is op return, and this will be your data. So this is the remaining data, as in this hash of the patch and any other data. This will be your whole script, and this will be placed within the transactions output as script, and the amount will be 0, and as input it will be say pointing to some account owned by the company A1. Some It will be owned by A1. So this is mainly to pay your transaction fee or something. It will be paid in Bitcoin, like Satoshis, and but this specific output, right, of this transaction, it is only it is just op return, and since it does not have any instruction to hash or verify the signature or anything, right, what happens is, the output of this transaction is unspendable. This is like an unspendable output, because the only opcode used in the output is op return. Only this is being used, and followed by that I have some data. And now how this can be used by all the other organizations which are looking at updating this application is, the company can just provide, okay, I have to, so this is the patch I want to update, the company will provide. And what they can do is, they can take the hash of the application, sorry, hash of the patch, and they can also, they can be provided with the transaction which is included in the blockchain, the transaction ID. And now the company can look at this transaction which is included in the blockchain. They will look at the script, if it's being included in the blockchain with this specific public key of the company and all those things, if they get to know, right, so they can certify that this patch is indeed correct, and it was generated by the actual company A1, and not some attacker who is fooling around and giving out patches in the name of the company A1. Okay, so this is like a, decentralized way of giving out patches, and it gives us like trust, because like you don't have to, you can easily verify whether the patch is indeed coming from the um, so whether the patch is coming um, uh, from the actual owning organization or not. So in this, it's like a transaction only, but they are using this op return opcode to store the information in the remaining part of the script. So the script size can be around, like, say, 300 bytes or something, right? So for 1 byte, they can have the op return opcode, and the remaining bytes they can store this data hash of the patch or anything they can store, and the output won't be added to the UTXO set. So usually when we say, whenever a new transaction gets generated, right, it would get added to the UTXO set in Bitcoin. So UTXO is unspent transaction outputs, right? But this specific output, if it just has the op return and nothing else, this is unspendable transaction output. So it is not like unspent, it is unspendable. So to save space and like not to bloat the UTXO set, which has to be stored across all the nodes, right, this op return output of the previous transaction won't be stored in the UTXO set. Okay, so this is one use case which you have, which is like not directly, which is not like sending X bitcoins from Alice to Bob, but instead it is mainly used to store the hash of something, store some data, and which can be used by others to verify whether the data is correct or not. Okay, so this is one like application I could think of, and so this is with respect to Bitcoin. um, in Ethereum, like once due to the smart contracts, there are like tons of applications which are which are possible, like other than just like sending money across the network. So in Ethereum, one is those NFTs and those things which are like sort of used widely, one application. And the other thing is like mainly in this example as well as the other examples, right? The main advantage of the blockchain is it gives like decentralized trust. So who is the owner of this particular data or something, it can be easily certified by storing it in a blockchain, and it can be certified by all the nodes in the network easily. So uh, I guess that's it. Is this okay to span?
Yeah, okay. Yeah, thank you.
Okay, cool. Okay. So in that case, any other doubts anyone else has?
I was just on one more thing.
Right.
This hyperledger, it's a permission, uh, like a permission model distributed setup, right?
Yes.
Uh, so I'm just trying to understand the use case. So so here actually only known people will be participating,
Ah,
and uh, and if they want to reach a consensus among themselves, the known people, then they will be using hyperledger, right?
right.
uh, so like I don't know, this is all I was just last week video I was going through.
Right.
There is also everything is explained in terms of transactions, like we are trying to send some I was just, I mean, my, is there any common application which day to day I can think of, okay, this can be an hyperledger I can use?
Uh, Day-to-day application. See,
Or any use case did he, because see everything what I say, uh, that whatever in the entire video it is being explained, we are trying to send money, alice trying to send money to bob, transaction is involved. But I keep hearing that, okay, this blockchain concept is generic, it can be used whenever you want a distributed consensus, this can be used.
right. So
uh,
yeah,
yeah,
I get
where
it.
are those examples, actually one such examples?
Okay. So this I studied long back. So in Hyperledger Fabric, if you look into GitHub, right, there is one example with respect to like they implement an voting system using Hyperledger Fabric. Have you come across it or you?
No, what is that?
No. So basically, they use this. So they implement an voting system where the votes are stored on the blockchain. So its
Mhm.
votes are stored on the blockchain, the Hyperledger the platform, and here the transaction uh, is not like sending money or something, but it's like say person A votes for someone, person A votes for someone. So this is what a transaction is,
Okay.
and your say your the client is the person over here. So this is the client, and they will interact with the blockchain, the Hyperledger Fabric platform, and they will submit a transaction. So submitting a transaction is like it will be like invoking a function, say vote vote underscore for, and say it will have the person's ID, say the voter ID or something. The symbol is voting for the party name or something, the candidate name. Okay, and this would be the transaction, and now the platform so this would be like a function in the smart contract function, which is stored on the blockchain platform. Okay, and now when we execute this function across all the nodes, the condition of this, the logic of this function would be such that one, to prevent double voting. So say the same client with the same person ID, it should not double vote. Okay, that is one condition. And second, the person ID should be valid, as in the voter ID should be valid, and all those things. So like some set of conditions will be there within that smart contract function, and once that is all over, this transaction would be valid. And then in the database, in the once this transaction is committed, right? This transaction is committed. There will be a state change, and by state change means what happens is so this candidate name for whoever the person noted, their vote will be incremented by +1. So this is what the state change, and the other state changes. This is one. The other state changes. This whatever whoever voted for this candidate, right? This person ID, their status would be set to voted. So again, if he tries to vote, it will be like double voting. So this would be part of your uh, ledger. All these details, all these state changes.
Okay.
And yeah, so this is one. So here the transaction is nothing but any function you want to invoke on the smart contract, or that would be um, composed as a transaction and sent to the blockchain platform. So
Okay.
this is one use case which it's the code is itself present in Hyperledger Fabric. The If you just Google Hyperledger Fabric voting system or anything, I guess it would be present on GitHub. The
Okay.
code and
And this one, it uses PBFT, right? This one, this
sorry.
icon. Does it use PBFT?
Okay. So
Okay.
it
Underlying.
can it so the cool thing with Hyperledger is it can use any of the consensus protocols. It can use PBFT. It can use Raft. It can use anything. It can say it can try to
Pax.
pass
Paxo.
laws, or it can use anything. Um, it can use anything. It can even, I guess, try to use proof of work. I'm not sure. Like, solve a puzzle and perform. Like, it can use anything, I guess. No, not proof of work. No, it can use any consensus protocol. The thing is, it's like pluggable. So everything in Hyperledger Fabric is pluggable. They have designed it in such a way that it's not tied to any particular consensus protocol or anything. It's just like a platform over which you are given full control over what each um, what each entity can be like. So so it is like sort of like open source thing. So you can, if you get an implementation of some your own consensus protocol, customized one, you can just make sure it interacts with that Hyperledger API properly, and you can just plug it in, link it as part of the Fabric platform, and deploy it.
Yeah.
Okay.
Just one more.
Yeah.
This there are very clearly demarcated like different kinds of algorithm. For example, permissionless public network. We have POW, POP,
Right.
POS. So all those algorithm, can it be used in Ledger? That's what you said. POW can be used. Um,
So
can they
actually,
be used? Yeah.
POS can be used in permission. So wait, POW, what does it do? So POW is you select a leader node which has to uh, propose a block, and be selected. So yeah, I guess we can use POW. I should double check on this. I'll just check on this. But what I understood based on reading Fabric is it can use anything. It can be POW. It can be POS also. So the way how Fabric is constructed, right? Um, it will say you have a client application over here. You have a client application. Let me just reduce the size. Okay. Okay. So say we have a client application. Is this visible, or should I increase the?
No, visible.
Okay.
It is visible.
Okay. So this is your client application, and it is written in any language. Say for now it supports Go, Java, Python, many I guess. So say it's written in any language, and this will be interacting with the Fabric SDK. So the software development kit, okay, like set of APIs. And now uh, say you want to vote for some person or something, right? You will use these APIs to interact with your actual Fabric platform, okay, and all your nodes, everything. So say node 1, let me use a different pen. Node 1, node 2, node 3, like that, so that like so many nodes would be part of this Fabric network, and your transaction will be submitted to this network, okay. And usually what happens is, if you look at the Fabric architecture, there are three types of nodes. So you know these, right? I guess it's covered in the lecture. Is it covered in lecture, these things?
Uh, yeah, we know peer. At least what I remember, peer channels, MSP.
Okay.
What are those node types? If you are talking, you just mention. Then I
Endorser.
know.
Okay. Let me
I
just.
don't know this acceptors. I don't know. Not in the context of ledger. I don't think.
Okay. Now let me just give like a brief explanation. So there are usually three node types. Okay. So one is the endorser, the other is the ordering node.
Orderer is there. Orderer, I think that I remember.
Okay.
Orderer was there.
So ordering node, and then we have commit the committing node. So this committing node is usually like all the peers should assume this role actually. All the nodes in the network would be assuming the committer role. But the ordering service and the endorser, only like a subset of nodes would be assuming this service. Okay. And every client application which is submitting a transaction, it will be having connection to at least like two or three peers, okay. So that will be like sort of the gateway to the entire Fabric network, the blockchain network, okay. It will have connection to say node 1, node 2 and node 3, okay. And say suppose there are like many other nodes also, and say once your transaction is submitted to the Fabric platform, right? So the step one is it submits the transaction to the Fabric platform. And the second step, what happens is the submitted transaction is given to your endorsing nodes. So what these say, like there are six nodes, N4, N5, and N6. So what the endorsing nodes will do is, say all these nodes are endorsing nodes, okay. And what these endorsing nodes will do is, it will execute your transaction, or execute that function, whatever is part of your transaction. It will execute it, but what it in so actually it don't execute per se. It will simulate your execution, simulate the execution. So what I mean by simulate is it will just see whether it succeeds your properly, but without changing the world state or any of the variables, without updating the state or writing to the disk. It will just update. It will just see whether your transaction succeeds without any error, and then what it will do is it will generate read write sets. So what say in this voting system transaction, like when I invoke this function vote for, right, what all elements are being read, what all variables. So one is the voter ID, whether it's valid or not, it will read like an voter table. And then whether and for writing it should update the status of the voter table. Again it will be writing to it whether the voter has voted before or not, like that. And then it will also update the vote count for that candidate, so the candidate table. So like totally like one item is read and two items are returned to. So this will be your read write set. It will include, okay, this specific data item or data array was read from, and these two data items were returned to. Okay, so this information will be generated by your endorsing nodes. Okay, and now what happens is there is something called as the endorsing policy. What this endorsing policy is that out of all the 6 endorser nodes, at least four of them, at least 4 of 6 endorser nodes should have the same result. Should have the same result and succeed. Okay, so so this policy, right, this is like custom, so it is not like fixed. So with respect to each type of transaction, say like in one case I'm voting for a candidate, in another case say like the administrator of that node, or administrator of the election, like the election committee admin guy, right, he might want to add a candidate name or something. So for that they can have a policy like all the 6 nodes, 6 endorsers should succeed, like that. Okay, so the endorsing policy will vary with each transaction type, with respect to each function, whatever is being invoked. So it's all like custom based. Okay, the endorsing policy can vary. Now, once these endorsers have seen whether it succeeds or not, and where it generates a read write set and all these things. Now what the endorsers will do is it will return back the response to the client. It will return back the responses to the client with all the endorsing with the read write sets, with all these read write sets. It will return back to the client, and that is what is known as the third step, which is actually um, return the sorry, checking the endorsing policy. Okay, now what the client will do is it will check, it once it receives all the endorsements, right, the endorsing nodes will return the read write set and also the output whatever it got, and the client will check whether the Fabric SDK, actually not the client, the Fabric SDK will receive all those responses, and it will check whether it follows the endorsing policy. The Fabric SDK would have been set with a specific endorsing policy based on the function which was invoked. And if that endorsing policy is successful, like 4 of the 6 nodes have replied positively, means then the transaction was a success. And now what the application will do is, this Fabric SDK is, it will step 4, it will submit the transaction to the ordering service. Now this ordering service will also part of the blockchain network, and say a subset of these 6 nodes are part of the ordering service. Say like assume this part is part of the ordering service. So they can, so each node can take multiple nodes. They can be like part of the ordering service also. They can be an endorsing node also, and they can be a committing node also. So each node can take multiple roles. So it's just up, based on how you want to design your system. So say you want to make it like fault isolation or something, right? You can keep your endorsing nodes separately, your ordering service separately, and instead of like having an overlap or something. So it's left up to you. Okay, so in this case, let's assume like N4, N5, N6 are the ordering nodes, and these transactions, whatever the endorsing policy, whatever the endorsing nodes responded back, right, to the client application, those responses would be sent to the ordering service along with the transaction. And now what the ordering service would do is it will order your transactions within a block. Order your transactions. Okay, it will just order your transactions. So so uh, finally what my goal is in a transaction, if it has to be added into a ledger. So in a Bitcoin also, uh, you will have like thousands of transactions which are being added into a block, but finally all those transactions would be executed simultaneously. So say like here I'm just say like person A votes for um, some person C, okay, and later another transaction is also there where person A votes for D. Okay, so the order in which this transaction is included in the block will determine which transaction succeeds and which fails. So if A votes for C is added first, right, I will set A as voted for C, and to prevent double voting, this transaction will be invalidated. But whereas if the ordering service had included A votes for D first and then A votes for C means, but to prevent double voting, this would be invalidated. Okay, so the ordering service can order your transactions in any way. There are multiple ways, but usually like first in first out or something is used. And for higher availability, okay, oops, for higher availability, your ordering service is the main crucial part. So up till this stage, right over here, step 1, step 2, and step 3, there can be many client applications, okay, many client applications running simultaneously, executing simultaneously, and submitting transactions to the endorsing nodes. But all these transactions now have to be validated, and in which order should they execute, that should be determined. And for this, all these transactions which have been endorsed by these endorsing nodes have to be submitted to the ordering service. So this ordering service is like sort of a bottleneck, because now all the transactions is given to the ordering service, and they have to order the transactions in some way, like first in first out, or in some way they order the transactions. So to avoid this bottleneck, for higher availability, and for also for better throughput and all these things, they can use like, and also to avoid corruption, and since your ordering service is the um, main entity which determines where in which order your transactions are executed, okay, so they will be they can be like a set of nodes, and you can use a PBFT consensus protocol among those nodes in the ordering service. Like so N4, N5, and N6, those three nodes can be part of can be like instantiated with a PBFT consensus protocol. And using this consensus protocol, the nodes would be the ordering service would be ordering the transactions, determining the sequence in which the transactions are ordered. And so this is step 4, that is ordering the transactions. And for higher availability and all those things, you can use a consensus protocol among multiple nodes. And in each round or something, each node can assume the role of a leader within the ordering nodes, and tell in which order the transactions have to be executed and all those things. And say if some node is crash or some fault occurs or something, to be fault tolerant also, using these PBFT protocol or RAF protocol or anything, any protocol can be used. Okay, so this is what I meant by pluggable. So it need not be PBFT. So instead of having N4, N5, N6 nodes, I can just assume only N6 is the ordering node. So all my transactions should be going to N6. But for higher availability and all those things, I can use multiple nodes and then use a consensus protocol among those nodes alone. So there are like lots of design consideration. The design space is so used, like I can do whatever I want, fine tune it with respect to any application. Okay, so that is one. And so this is step 4, that is ordering the transactions. And once my transactions have been ordered, what will happen is, in this is step 5. Step 5 is the ordered transactions, okay, would be delivered to all the nodes. And it will be delivered to all the nodes in the network. So mainly this will be the committing nodes. Okay, so the committing nodes, usually all the nodes in the network assume take the role of a committing node. And step 6, what happens is the committing nodes would then validate your transaction. Okay, and what I mean by validating a transaction is, say um, uh, uh, what they mean by validating is, this block of transactions is given to given so this block of transactions, okay, so this block is given to a committing node. And now say within the same transaction there are within the same block there are two transactions. One person A voted for person C and person A voted for person D. Okay, and these two transactions will have a corresponding read write set, okay, which is being endorsed by a set of endorsing nodes, like for at least 4 endorsing nodes. Now this read write set, okay, uh, the read set over here for this specific transaction would be like it is reading A's status whether it has voted or not. This will be the read set, and the write set would also be it is updating the A status, that is it has voted for C. Okay, and so this is the read write set for this specific transaction. And now for this specific transaction, so this is first and this is second. For the second transaction, the read write set is also the same, since A is the same voter ID and it's voting for D. So the read set would be reading from A, and the write set is updating A status. It has voted, A sorted. But the issue is you're updating. So whatever it has returned, right? So it's sort of like prevent double spending. Okay. So the same way, what happens is only one of these transactions is valid. So what happens is the issue over here is these two transactions, the endorsing nodes, okay, when they were submitted to the endorsing nodes in step 2, these two transactions would have been submitted by two different application instances. Okay, that same voter, he could have used two different application instances, and it could have sent two transactions, say at the same time or something, to the fabric network. And what would have happened is the endorsing nodes would be split up in such a way that, like, one set of endorsing nodes would have endorsed transaction 1, and the other set of endorsing nodes would have endorsed transaction 2, and both would have looked at the world state at that particular time, that is A had not voted before, and they would have executed that transaction, and they would have generated a read write set. Okay, note that the world state is not updated by the endorsing nodes would just have simulated the transaction. They wouldn't have concretely updated or any variable. They would have just generated the read write set and simulated the transaction and whether it succeeds or not. But since both these transactions would have gone at the same time, were submitted at the same time, the world state or the blockchain from which the nodes were reading information, right, where, like, whether A has sorted before or not, that would have been set to false, and both these transactions would have executed. Now at this validating step in step 6, okay, my a previous transaction is um, writing to A status, and simultaneously another transaction is trying to read from A status. So this somewhat like a read-write conflict. So if you have looked into database or anything, like, so some transaction is trying to write into a variable slot. At the same time, another transaction is reading from a variable slot, and is sort of like a race condition, like, okay. And to achieve serializability, so either if a write occurs, then the read should not occur actually. So this read is occurring because this specific transaction is valid. A is voting for D is valid only because the initial condition, whether A voted or not, was false. The initial condition is A as voted previously was false. But since this status over here is updated by transaction 1, so the read set of transaction 2 is disturbed actually, because transaction 1 is writing to that read set. So the read set is being disturbed by the previous transaction. So the committing node, what they will do is, once they have executed transaction A, this transaction 1, when it reaches transaction 2, it sees that the read set is disturbed by a previous transaction, and it will invalidate this transaction. It will invalidate this transaction, and it will mark it as an error. Okay. And now what happens is, within a block, okay, within a block, there will be set of valid transactions, okay, and as well as invalid transactions. And note that in, say, Bitcoin or Ethereum, right, usually only a valid transaction would be included in the block. But in Hyperledger Fabric, what they do is they include both valid as well as invalid transactions. Okay, they include both, and they update the status. They mark it as like 1 for validated successful transaction and 0 for like false or something. And once this validation is done, right, what happens is step 7. Step 7 is publishing the result. So by publishing is, the client has to be finally be given whether the transaction is like succeeded or it failed. Okay, so this, the committing nodes, okay, the committing nodes would publish the result. As in, it would send a result to all the other viewers, and one of those peers would be in connection with your client application, and the client application would be client notified of the final result, whether the transaction succeeded or failed. And the key point which I missed is in step 6, right, when we are validating the transaction, okay, if the transaction is valid, right, what happens is the world state is also updated. So, as in the status of whether A had voted before, the person A had voted before or not, this should be set to true. Okay. Uh, the key point is in step 2, when the endorsing nodes actually simulate the execution, they don't change any of the variable states. They don't actually write into. They just simulate the execution, go step by step. It's similar to actual execution, what is done in step 6, but none of the variables are touched. They are not changed. It just generates the read-write sets alone. These read-write sets are alone generated, so that finally at the end, when the validating step comes, right, in step 6, these read-write sets are sort of telling the committing nodes under what condition did the endorsing nodes simulate a transaction. And if after executing say 100 transactions before, if this specific transaction, whatever, like A is voting for D, if the condition under which the read write set, the conditions under which this transaction 2 which was simulated by the endorsing nodes is the same uh, after executing 100 transactions also, then it is valid. But here, since I'm executing this A to C transaction before, A is voting for C, the read write set, the condition under which transaction 2 was endorsed by the endorsing nodes is invalidated, is wrong. So it is disturbed actually. And because of that, the transaction 2 is invalidated, and it is like a failed transaction. Okay, so this is the overall transaction workflow in Hyperledger Fabric, and yeah, this is it. And any doubts in the transaction workflow in Hyperledger Fabric? Okay, so the main thing is you have your endorsing policy and your the ordering service, and then your commit. So if you look at a high level overview of how these the transaction workflow is, step 1 is you get your endorsing policy, which sort of like simulates your transaction. Okay, this is one. And second, it provides to the ordering service, and finally it does the validation. So this is the 3 steps. This is what happens in a Fabric transaction workflow. Compare this with what happens in Bitcoin or Ethereum. What happens in Bitcoin is, first you actually order your transactions. So once say the miner node is given the transactions, it will be the miner node will collect all the transactions, and the miner node will place it in a block. So it orders the transactions and then it validates. Okay, so by validating, actually what happens is it executes. Okay, so step say 1000 transactions are included in a block by a miner, means the miner will execute starting from the first transaction. It will serially execute each transaction, and after in like executing the transaction, it will also update the ledger, as in the UTXO set or the world state. It will update the ledger. Okay, so this is what happens in Bitcoin or Ethereum. But in Hyperledger Fabric, what is being done is this execution stage over here. This stage over here, oops, this stage over here, execution stage, is split and is kept in the endorsement stage as step 1. And the reason why this is done is for increasing your throughput. So this, since this Hyperledger Fabric is aimed at enterprise applications, right? The number of transactions per second which has to be committed is to be like very high, around like 10,000 transactions also. And for doing this, most of the time, which is like some aspect in this transaction workflow has to be parallelized. And what can be easily parallelized is this execution step. So what is being done is the transactions are being simultaneously executed or endorsed by all the endorsing nodes, and um, it is given to the ordering service, which then orders the transaction. Okay. And since this like multiple client instances, they can like submit multiple transactions, and there is no like bottleneck in this stage. Okay, it's just like how much capacity the endorsing nodes has. So this stage increases the throughput actually, and this will increase the number of transactions which are executed simultaneously. In Bitcoin or Ethereum, the transactions have to be executed in a serialized fashion, starting from the first transaction till the last transaction which is included in the block. But here, the block concept itself, the ordering stage, is done only after the execution. Okay, so this is where it increases the throughput actually. And but you might argue that okay, like here I'm executing simultaneously in the first step, that is the endorsing policy. But finally, how is it so finally, like each transaction, when it's included in a block, it has to be in the same way how it was executed sequentially, not simultaneously. So for that only they do the ordering service, and finally they do perform the validation. And notice that in the endorsing or the first step, the execution, right? It just simulates the transaction. That's the key novelty. It simulates. It does not update any of the variables. So it's safe in that aspect. It can safely go and simulate the transaction, all the transactions simultaneously, and those which are having conflicts between them, those will be invalidated, and the remaining can be validated. Okay, so this splitting of the execution and the updating the actual ledger. So updating occurs in the validate stage, and the execution happens, the simulation happens over here. Note that the committing nodes, okay, they do not execute the function again and again. They don't execute. They just look at this read write set. So that's the importance of the read write set, which is generated by the endorsing nodes. The execution is only done by the endorsing nodes, and it generates a read write set based on which alone the committing nodes can validate the transaction. Valid or invalid, it can decide. And this can be done very efficiently. Okay, so this is the fabric architecture, and the this is the overall idea of how a transaction is submitted to the fabric architecture, and it is committed, it is validated, and the changes are reflected in the blockchain ledger. Okay, any doubts in this transaction workflow?
Uh, just one thing. You said that the endorsing policy, if there are six, are there at least four.
Right.
Uh, but as per the PBFT discussion algorithm, if there are F faulty nodes, there has to be 2F plus 1, at least 2F plus 1, uh, uh, more number of, I mean, yes, for example, if somebody says no, but 2F plus 1, we got yes, then
Okay.
2F plus 1 should be considered as consensus.
Okay.
So, so 6/4, whatever you explained,
Ah.
is that applicable for ledger,
Ah.
or it is follows the PBFT?
Okay.
Uh,
Good question. So when I this PBFT actually comes under the ordering service. Okay. So the PBFT, I guess it doesn't it doesn't have anything to do with your endorsing policy. So the ordering service is the one, like say you have multiple nodes, say like around 10 nodes or something, okay? And among these 10 nodes, something can be faulty, some can break down or something like that. And all these 10 nodes should agree in the way the transactions is ordered within a block. So whether transaction A comes first or transaction B comes first, all the 10 nodes should accept. And this is what the ordering service has to be is responsible for, and this is where you can use any consensus protocol among the 10 nodes for better availability and for fault tolerance. So this is where the consensus protocol is actually used. The ordering service is your consensus protocol, the pluggable interface. The endorsing policy is actually for execution alone, and here actually you don't require any there is no concept of consensus in this endorsing policy. It's just like whether you want it to be fully secure, you want maximum security, as in all my endorsing nodes have to return the same result, or it's okay like any one endorsing policy endorses my transaction. It's left up to your use case. So your PBFT consensus, those things, that consensus protocol has nothing to do with your endorsing policy. It's fully associated with the ordering service only. The endorsing policy is just based on your application. Say if some important change has to be done into the blockchain ledger, right? Say this voting for some person or something, right? Then it is better that all the endorsing nodes execute that transaction, simulate it, and return back the read write set for higher security. Um, but say you have a transaction which is just reading some elements, it is not writing. You all just want to look into the blockchain and see whether say you want to see whether A has voted before or not. You are not voting, but you just want to see whether we have voted before or not, means you can just submit a transaction like view status, and in this view status transaction, when the endorsing nodes executes, right, the write set would be empty, but the read set would be filled in. Okay, and this transaction you need not uh, the endorsing notes, the endorsing policy would be like just like say two endorsing notes can execute and show something like that. And this view state, this transaction, whatever the response from the endorsing node, the client need not submit back to the ordering service, because I'm not changing the write set at all. I'm just looking at the information whatever is present in the blockchain, so it is not submitted also. So the endorsing policy is nothing to do with your PBFT or consensus, based on my understanding. The ordering service is the one which is crucial, and this sort of like a bottleneck actually. And there only the PBFT or the 3F plus 1 nodes, those conditions all should be applied.
Okay, thank you.
Okay. Kandar Shah has raised his hand. Yeah, Shah. Uh,
Yeah, actually, I'm like having an issue with the installation of Get platform on my laptop. So how can I do that? If you can just share the steps of that, because that is not available in like any of your lectures. So if you can guide on that part, it is like basically for the uh, uh, means week 5 Ethereum 2.
okay.
So I cannot install that particular platform, and it's like I cannot use that particular code. So if you can guide on how to do it.
So did you follow whatever instructions are present in the video lectures? Because it's pretty straightforward actually. Are you doing it on Windows or in Linux?
Windows. Windows.
Within virtual, are you using like a virtual image of Linux or
No, nothing as such, because I don't know, because over there there was like no steps mentioned. So I was just downloading it from that particular platform, and then I was just installing it.
no, because in the video lectures it is based on Linux OS. So if
Okay.
you want, like since you are on Windows, two ways. One, if you want to just follow the video lecture, whatever they do, you
Yeah.
can download VirtualBox and install Linux OS, like say Ubuntu 18 or 20, install it,
Okay.
and within that you replicate the same steps, you follow the same steps shown in the video lectures. That is one.
Okay.
Or
Okay.
second, so this would be like sort of slow, not very slow, but like based on your mission speed and all those things. But if
Okay.
you want it to be like natively running on Windows and you want to be doing that, means you can easily Google and see actually, because
Okay.
Ethereum get, and they will support of course Windows, I guess. So there will
No,
be
because
many of them.
no, actually, I was just downloading. I get from that particular website. I get Ethereum.org, but
Okay,
it was not working with that.
okay. I'm not sure then, because even I have like a Linux system only, but
Okay.
so even if many of them have raised queries, like it's not working on Windows and those things. But yeah, like usually like development environment, like open source software, right? Ethereum, so they,
Uh huh.
it's like Mac OS or like they use Linux OS. So like Windows is would be definitely supported, but
Okay. No, because I was downloading that particular file only the for the Windows. I
right.
get v1.11.4, but it is not uh, not going through
But then you can try this virtual box method.
VirtualBox, right?
So if you come into, if you face any error, also you can easily Google, and there'll be definitely multiple Stack Overflow help pages or multiple pages, so you can
Okay.
easily
Oh,
Google it and see.
okay, fine. Thank you so much.
Yeah. Cool. Okay. So any other doubt?
Can we download this video? This whatever the video is available.
Sorry, which video?
The lectures video.
Uh, I didn't get
Uh,
whatever professor explains the video.
yes, 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 yes.
Yeah, you can download. I just open it in YouTube and like download in
Okay,
YouTube.
but that YouTube link, how to get it? Because I see when I there is a download option. If I go and click, it is taking somewhere some other page,
No,
and
like within that thing, like there will be it will be like week one, week two, like that, uh, like a sidebar, right? And when you click on week two, there will be like five videos, and you click on one, there will be like one video. And you click on play over here, there will be like a YouTube icon.
that link we need to get it there.
No,
Okay,
if you
let me
just
check.
click on this, you will be opening like a
Okay,
new tab, and
okay, okay.
it will be like
Oh,
youtube.com, and
okay.
from
Let
there
me.
you can just
No,
click on the
no
YouTube.
need to go to YouTube also. We can download directly using that if you are login with our ID, like any
Ah,
Google
yeah, you
account.
can just copy that URL also. I just click
You
on
can
YouTube.
yeah.
Yeah,
Okay, okay, okay. Thank you.
okay, cool. So in the forum, some of them have asked me to explain PBFT algorithm. Okay, so I'll be explaining that. Before that, anyone has any other doubts?
Hi, sir. Sign Bill. So actually, I just want this practical approach of this also. Means this algorithm of PVFT algorithm, how we are using in practical.
Sorry.
this PVFT algorithm, whatever the algorithm we are discussing, so how we get the practical approach for this means in application, how we are utilizing this,
How it is being used?
right, in
Okay.
enterprise level, in any application. And
No, so okay, okay. Yeah. So PBFT, the main, so PBFT is practical Byzantine fault tolerance, right? And uh, just like a bit of background, uh, many of you might know, like those who attended my previous sessions, you would have known this. So one thing is there is this FLP impossibility theorem. Okay. And what this FLP impossibility theorem states is, um, if you have an asynchronous network, okay, an asynchronous network as in, like, say you have 100 nodes, and if you send messages between the nodes, there is no guarantee that it will be delivered within a day or so. It can take it can take like a month or so also, but eventually it will be delivered, but you don't know when it would be delivered between two nodes, any message you send. So that's what an asynchronous network is. Okay. And if you have an asynchronous network, and say if you have n nodes in the network, okay, if n nodes in the network, and out of these n nodes, even if one node, oops, even if one node in the network is faulty, okay, then no possible consensus, then no consensus can be reached among the n nodes. So this is what the FLP impossibility theorem states. Okay. And if you look at say synchronous networks, if you look at synchronous networks, uh, out of n nodes, right, even n minus 2 nodes can be faulty. The remaining good two nodes, the honest two nodes, would be in consensus. Okay. So this is the theorem in a fully synchronous network. So synchronous network is, say if one node sends a message to another node, it will definitely reach in 1 minute or 2 minutes. Some time bound would be there, and that's what synchronous network is. So these are the two extremes actually. One is the asynchronous network, and the theorem states that even if one node is faulty, there won't be consensus among the nodes. And in a synchronous network, out of n nodes, even if n minus 2 nodes can be faulty, my remaining two honest nodes will always be in consensus with each other. But in a real world scenario, a fully synchronous network is not possible. There will be network outages in between. So I cannot assume that I cannot work I cannot design a protocol with this asynchronous network model, because this FLP theorem states that even if one node is faulty, then I cannot reach consensus. So I should have like a trade-off between asynchronous thing. I should be like in between these two models of network. So for that, what the researchers came up with is called as a partial synchronous network, where for some time t it will behave synchronously, like it will behave synchronously always. Okay, it will be always, most of the time it will be synchronous, but for some time t, say like there will be an upper bound, as in like some say 1 hour or something, 1 hour or something, it will be asynchronous. Okay. and after that 1 hour again it will revert back to synchronous model. So it is typical of a real world network. Say some network outage happened in Airtel network or something, Geo network, within 1 hour or maximum 1 day or something, your network cables, everything would be fixed and your network would be working. So this is sort of like a realistic model. And now since this you have like a synchronous phase followed by an asynchronous phase followed by again a synchronous phase, like that, right? So now this FLP impossibility theorem will not hold. So now even if one node is faulty, it won't disturb the consensus among the honest nodes. So this partial synchronous network was developed. This model is used in order to avoid this FLP impossibility theorem. So this is the background behind PBFT consensus. So not sticking with a fully synchronous network and having an idealized setting, but at the same time not having like a fully extreme setting of asynchronous, but having a realistic setting of a partially synchronous network. Okay, so this is the network setting of a PBFT protocol. And uh, based on this, now let's look at what the protocol does. So before looking at what the protocol does, okay, we should first look at what's the aim of a consensus protocol. So usually what happens is in a consensus, the application, right? It can be any application. Say you have nodes, uh, 6 nodes, okay. So N1, N2, N3, N4, N5, N6, okay. 6 nodes are there. And now say a client comes and say you are having like a distributed uh, a YouTube service, okay, YouTube service or something, YouTube video service, where you can add subtitles to your video, you can make clips, okay, you can do whatever you want, you can delete parts of your video, something. And now say client has a video of like a blockchain video, some video about some video he has, say VID1, and this is replicated across all the nodes, okay. So this VID1 is replicated across all the nodes. And now say the client has to execute a function, and part of that function is starting from starting from a specific clip in the video, like the first say the last 10 minutes I have to delete, last 10 minutes I have to delete. And what he does is he submits this transaction, this function, he invokes it and submits it to node 1, and node 1 what it does is it deletes the last 10 minutes. So initially say it was for 1 hour, means everywhere it's for 1 hour, the video initially, and now node 1 alone it deletes it, and now it's for 50 minutes, okay. And now say the client, say this client, right, some other person also has the same access to the same email ID of the client and anything, right, or like this video, like someone else wants to view it from some other location, and that location is now say they are accessing node 2, and when they access node 2, they should not get this 1 hour video, instead they should get actually this 50 minutes video. And now the aim of consensus is this, whatever application, whatever transformation I did on this video on node 1, it has to be replicated across all the nodes, okay. And it has to be replicated across all the nodes, and all the nodes should have the 50 minutes video, such that later, after immediately after some 10 minutes or something, once a new client or someone wants to view this video from some other server, means it should return a synchronized copy, that is that 50 minutes video and not the old copy of that video having 1 hour content. So this is what consensus is all about, and this is what consensus has to achieve. And either the goal of consensus is either if n1 tells that this transaction, this node 1, if it succeeds in editing the video, cutting off the last 10 minutes, means all the other nodes should also chop off the last 10 minutes, else the transaction should fail and all the nodes should have the old 1 hour video. Okay, so either, so the output of your transaction, the output should be either all nodes have 1 hour video or they have 50 minutes video, and this should occur across all the nodes. Okay, so it should all accept together or it should all fail together. It should not be like node 1 and node 2. Node 1 alone has 50 minutes video and all the remaining 5 nodes will have a 1 hour video. This is inconsistent. So consensus aims at generating a consistent view. So this is the main aim of consensus. So all nodes should have the same result. Should have the, whether it should succeed together or it should fail together. That is what consensus is all about. Okay, and in an ideal scenario, all the nodes should be working, but in a real world scenario, there will be faulty nodes. Okay, and faulty nodes can be different types of fault. They can act maliciously, or there can be network faults in between, or there can be like the node can be like crash in between, like crash fault. Okay, and researchers, instead of having um different protocol for each of these different fault, what they did is they clubbed all these faults together as a Byzantine fault. Anything, any fault, it will be coming under a Byzantine fault. Okay, and in order to make your consensus protocol, so the consensus protocol is the one which is responsible for having this consistent view, and this consensus protocol is, say, like when n1 receives this new function invocation and does this 50 minutes 1 hour to 50 minutes transformation, right? This consensus protocol is tasked with all the is responsible for replicating this changes in all the other nodes, communicating with all the other nodes what has to be done and all those things. But say if some fault occurs, right, the protocol should not fail, but instead it should ensure that a consistent view is reached. And for that, the consensus protocol has to be fault tolerant. Fault tolerant. So now PBFT algorithm is actually a consensus protocol which is Byzantine fault tolerant under what network model is a practical network model which follows a partial synchronous network model. And the two aims of the consensus protocol is, one, it guarantees safety, okay, which is consistent view. Okay, so safety in other words is actually all my honest nodes are consistent. Note over here, I am worried only about what my honest nodes accept on, whether they are consistent or not. I am not worried upon about the faulty nodes. Okay, so this is what safety in a consensus protocol is about. All my honest nodes, this notion over here is important. All my honest nodes are consistent and they accept the value or they reject the value together. Everything is done together. So this is safety. And the second thing is liveness. Okay, so liveness is about it. Eventually, it adds value. updates, or eventually it adds or updates. So any protocol, if the client keeps on submitting transactions or functions, those functions would eventually be added or updated to all the nodes, and they will all be updated, and they will be having a consistent view. The importance of liveness is because if liveness is not there, right, say I don't want to achieve liveness, what happens is, if say the consensus protocol just wants to achieve safety, means the condition for safety is all my honest nodes should be consistent, that is they should all accept or reject together. And a trivial way to achieve safety is, irrespective of whether a function succeeds or not, I will always return it as a failure. Now what happens is, all the nodes would be having like an empty ledger, like an empty state. Like initially, say all the nodes are having like a 1 hour video, means irrespective of what my client submits, whether I want to cut a clipping or add a clipping or anything, my consensus protocol by default will reject that transaction. And by rejecting that, what happens is, all my nodes are having a consistent view only, that is all my honest nodes are consistent. And the the but what happens is, it is becomes stale, as in the client transactions are not accepted anymore. So but still safety is there, because there is a consistent view among all the honest nodes. So that's like a trivial way of achieving safety. To avoid that, in a formal specification only, the the liveness property was introduced in a consensus protocol. So the main aim of a consensus fault tolerant protocol is both it should achieve safety as well as liveness. So together only it will be uh, a proper consensus protocol. Any doubts till now? The aim, what the consensus protocol has to do, what it wants to achieve, and the goals of a consensus protocol. Any doubts? Okay. If no doubts, then let's move into how the PBFT algorithm works, the consensus protocol. Okay. So in a PBFT consensus protocol, the there is something called as so there are say there are 100 nodes. Okay. Out of these 100 nodes, every so this is like a permission setting, and you know the identity of all the 100 nodes which are participating in the network. And say out of these 100 nodes, how the PBFT consensus protocol works is, say over here, uh, uh, okay. So say you have the client, okay, and there are N1, N2, N3, like that, N100, okay. 100 nodes are there, and now a client wants to submit a transaction which deletes the last 10 minutes video. So let that transaction be like transaction A. Okay, it clips the last 10 minutes, deletes the last 10 minutes. Okay, now delete last 10 minutes. Now this transaction A would be submitted to a primary node. Okay, and what the PBFT algorithm does is, it goes in, in sort of round. Okay, so round starting from 1 till some number n, it keeps on going. Okay, and what happens is, since this is a permission network, each round 1, round 2, like that, each round will have a leader node, a leader or a primary node, and this primary node would be responsible for reading the client request uh, and propagating that request to all the other nodes. propagating to all the other peer nodes. So any transaction which has to be included in the ledger, or which has to be executed, right? Some node has to be some node should be proposing that function. So here the client is getting the transaction, getting that function, and it is providing it to some node, and that node, say in round 1, if currently it is round 1, means it should give to node 1. And usually in PBFT, how the leader is determined for each round is the round number mod percentage the number of nodes. Okay, so say if it is the 1000 round means, and say if it is like 100 nodes, then it is like node 100 is the leader, percentage 100. Okay, so node 100 would be the leader. So each round, since I know the identities of the nodes before, and since it's a permission network, each round would be there, and in each round there will be a leader to whom all the clients would be submitting the transactions, would submitting the functions, and that leader would be uh, propagating that transaction to all the other all the other nodes in the network, all the other 99 nodes. And since it's a permission network, I will know the identity of each leader. The client will know based on, the client can request which round currently it is in, the consensus protocol is in, and based on that response it will know which node is the leader, and it will submit the transaction to that particular node. Okay, so this is the high level overview of a leader and all the other nodes. So the other nodes are called as backup nodes. Okay, and now what happens is, so you have two types of node in a round. One node would be a primary node or leader node, okay, and the other nodes would be backup nodes. And now all these nodes together should be in a consistent view. Okay, so by what I mean a consistent view is, the primary node would be proposing new transactions, whatever is submitted by the client. Okay, and all the nodes should either accept or reject those transactions, and the client should be notified of the result. Okay, and this is what the PBFT consensus protocol is trying to do. And how it does is, it does this in 3 steps. So currently, let's assume it is in round 1, and so node 1 is the primary node to which the client is submitting all the request, the transaction request. Okay, let's draw like this. Okay, and now let's this is the client, this is node 1, node 2, like that, node 99, node 100. Okay, and now say the client is now submitting a transaction, and it is submitting a transaction which is say like clip the last 50 minutes of the last 10 minutes of the video or something, and node 1 is the leader. And once this transaction, node 1 receives this request to perform something, to execute something, what node 1 does is, it will start a phase called as the pre-prepare phase. This is phase 1, pre-prepare phase. So in this pre-prepare phase, one second. In this pre-prepare phase, what node 1 will do, being the primary node, right? Step 1, sorry. Okay. Step 1, it will receive the transaction, it will receive the request or transaction from the client. Step 2 is it will assign a sequence number, So say it is sequence number, currently it is 100 means, it will like the last used sequence number is 100 means, it will assign sequence number 101 to the request, to the message M. So say this client request is denoted by R or something. Okay, this is R means this R would be assigned sequence number 101, and step 3 is the it will propose this request to all the other nodes in the network, that is it will perform a broadcast, So now what happens is this sequence number along with the request, okay, and the signature of the leader node N1, all these things it will be broadcasted to all the other nodes. Okay, so this is what is the phase 1, which is pre-prepare phase 1. And now what happens is, this is the next phase. Once all the nodes have received a pre-prepared message, right? Now this is called as the okay, sorry, that's a spelling mistake. Pre-prepare. So now it will be phase 2. Phase 2, which is the prepare phase. Okay. Now in prepare phase, what happens is, step 1, first it should accept, all the other nodes should accept the pre-prepare request sent out by the primary node. Okay, so accepting means it will check for some conditions. First it will see whether the identity of the primary node, whether it will validate the signature. So validate the signature of the primary node, whether it's coming from the correct leader. So all the nodes should know this is round 1, and in round 1 node 1 is the leader. Say if it is in round 3 and node 1 is sending a pre-prepare message, means it is wrong, because in round 3 node 3 is the leader and not node 1. So based on the round, it will validate the signature of the primary node of that pre-prepare message, and if it's correct, then what it will do is it will check whether it has received a pre-prepared message of the same uh, uh, round number, round comma sequence number. So say in round 1, currently it is in round 1, and I am assigned the sequence 101 to this request. um, Let me just do request REQ, okay, and currently it is in round 1, request 1, sequence number 101 is assigned. Okay, so it will check whether it has already seen round 1 101 before itself. It has already seen a um, uh, pre-prepare message with the same sequence number in the same round. If it has seen a previous pre-prepared message already, then it will reject the current pre-prepared message. Else it will else the all the conditions would succeed. Okay, so here this is the first time the primary node is sending out a pre-prepared message with 101 as the sequence number in round 1. So all the conditions have passed, and once all the conditions have passed, right, step 2 of the prepare phase is the nodes, each node will multicast prepare a prepare message. And what this message will be containing is, it will be containing the request of the client. So it will be containing like round 1 sequence 101 is the sequence 101, and the and each node would have signed this message, the signature, the digital signature. And also it will be and also the digest of the message, like the message contents, the actual the request contents. So this is like sort of like, you can assume it to be some metadata. Okay, so this is what a prepare message is, and this prepare message would be sent to all the other nodes. So it's sort of like a multicast, like all the other nodes in the network N2 to N100 would be sending out a prepare message to all the other nodes. So it will be like this. So N2 would be sending to N3, N4, N5, N100, and similarly this would be sending to all the other nodes. Like that, it will be like a complex web of, like N100 would be sending to all the other 98 nodes, N99 also would be sending to other 98 nodes. So what happens is, all the other nodes would be receiving all the other nodes, every node would be receiving all the other nodes uh, prepare messages, and these messages would be sent only if these conditions pass. That is, I should not have seen a similar pre-prepared message having the same sequence number in the same round, and the signature, all those things should be validated. And now what happens is, once in step 3, okay, so this is sort of like a crucial step where once a node receives majority, which is more than 2/3 of prepare messages, okay, once a node receives a majority, that is more than 2/3 of prepare messages, it enters into what is called as the prepared phase. Okay, so once after all these messages, this set of messages over here, once these messages have been multicasted to all the other nodes, and now all the other nodes have received means, then it will check whether majority of the nodes, okay, so one point I missed, node receives majority with the same result. Okay, so same result as in, majority of the nodes are having the same round number, so which is round number 1 comma sequence number, that is 1 comma 101 under other metadata. So if this is the content of the prepare message, okay, and if if a node, okay, if a single node receives majority of the same prepare message, oops, majority of the same prepare message means it enters into what is called as the prepared phase. Okay, and this prepared phase, each of the node would be entering if it receives a majority of the prepared messages. Say node 1 first received majority of the prepared messages, means more than 2/3, n1 will enter first into the prepared phase, and later say n100 receives, after some time it receives the prepare messages, means n100 will also enter the prepared phase. And note that whether a node entered a prepared phase or not is maintained locally, like node 1, if it entered a prepared phase, it won't know to node 100, it's something like maintained locally. Okay, so this prepared phase depends only if it succeeds only if it is entered only if a node receives majority of the same prepared messages. So why is this prepared phase important is once a node reaches a prepared phase means then it is confirmed that um, so what we achieve by this by sending out these two sets of messages, right? Prepare and prepare messages. When we tell prepared of say node 2 enters a prepared phase, and specifically what we tell is in round 101 sequence number for a specific message for a specific request R, it has entered node 2 has entered the prepared phase, means it has received 2 by 3 more than 2 by 3 responses from the other nodes. A majority of responses it has received, majority of prepared messages it has received from the other nodes having the same content, that is round 1 the same request is assigned the sequence number 101. By having this prepared phase, what's the uh, ultimate um, result is there is no other, what we can prove is there is no other non-faulty node which is in a prepared phase with the same round slash sequence number but a different request. Okay, so the thing is, say N2 enters into a prepared phase with respect to round 1 sequence number 101 and request R, means node 3 which is also non-faulty would not enter into a prepared phase where with respect to same round same sequence number 101 but a different request, say R2. This is not possible at all. Why? Because if a node enters into a prepared phase, what it means is majority of them should have responded with the same prepared message. So here, if say N2 received node 2 received a majority, okay, so out of 100 nodes, node 2 received 67 responses back from all the other 67 nodes. Node 2 received 67 responses which all accept the fact that in round 1 sequence number 101 is associated with request R, and node 3, say if this is true, right, if node 3 also is in a prepared phase but with the same sequence number and same round number but a different request, so then it is like 67 responses. So it received like a majority of responses from the other node. So like what we are trying to tell is what's the importance of having this prepared phase. If a node enters into a prepared phase with respect to a particular sequence number and round number and the specific request, right, no other node, no other non-faulty node in the network would be in a prepared phase with a different request with having the same sequence number. And how we are proving this is, say two nodes are there, node 2 and node 3. They are having the same sequence number but they are entered into a prepared phase with a different request. So this has entered into request R1 and this is sequence number 101 is associated with request 2 with respect to node 3. And if both have entered the prepared phase, means it has received a response from 67 other nodes. Okay, like more than 2/3 of the majority, 2/3 of 100 nodes is 67. Okay, so now it has got a majority response and both have entered into a prepared phase. But we have to prove that this is not possible at all. If it is having the same sequence number 101 in the same round, means R1 should be equal to R2. R1 cannot be equal to R2. This we have to prove. And how we prove is we look into how many nodes have voted for the have done like a double voting. That is, they have responded to both R1 as well as R2. Okay, as in like they have responded to both N3 R2 as well as N2's R2. So if you draw sort of like a Venn diagram, right? So this is sort of if you draw like a Venn diagram, and the total number of nodes is 100 nodes are there. Totally this is 67, and this is also 67, and the number of nodes who have not voted for um, the number of nodes not voted for request R2, that is they have not replied for replied to node N3 is 33, and number of nodes not voted for R1, that is it did not reply to node 1, not node 2. Okay, node 2, that is also 33. So 33 nodes, so 100 minus 67. Okay, so this part is actually um, 33, and this part over here, this is also 33, because those which have just voted for either one of the other nodes. Okay, so 33 and 33 nodes, so 33 nodes have voted for request R2 alone, and nodes that have voted for request R1 alone is also 33, and we know that the total node is 100, and if we subtract 33 from 100 two times, right, we get 34. So 34 nodes have actually voted both for R1 as well as R2. That is, they have responded both to node 2 and node 3, and that is, they have voted for both request 1 and request 2 and assigned a sequence number of 101. So 34 nodes have been like sort of voted for both the request. Now in a consensus protocol, for a particular sequence number, a node will vote only once. Okay, here the condition itself is if it has to like um, generate a prepare message, right? If a node has to generate a prepare message, or if it has to um, uh, uh, validate a prepare message, it will check whether the sequence number is already allotted to a request or not. And if R1 is already allotted a sequence number 101, any honest node would not allow a new request to be assigned the same sequence number, right? So all honest nodes would only vote once for a particular sequence number. But these 34 nodes which I voted for both the request and assigning it the same sequence number 101, these 34 nodes are actually faulty nodes. Okay, but here we have the assumption, but here PBFT follows an assumption that minimum if F nodes are faulty, right? F nodes are faulty means the total number of nodes should be more than 3F plus 1. So here if actually that is less than 2/3 should be faulty. Only less than 2/3 should be faulty. More than 2/3 should be honest. So out of 100 nodes, okay, less than 33 nodes are only faulty. Faulty is actually less than 33 nodes. But here 34 nodes have actually been faulty, which is actually against our assumption of less than 33, and in that case this out of this 34 at least 1 to 2 nodes would be honest. So any honest node would not double out, as in it would just either support R1 or it would support R2 alone. So in that case this situation is not possible, that is no two non-faulty nodes would be in a prepared phase, that is would not have received a majority of prepared messages having a same sequence number but a different assigned to a different request. So this is what the prepared phase is all about. A prepared phase guarantees you that if a node enters a prepared phase, then all the other non-faulty nodes would also have entered the prepared phase, and it wouldn't have assigned a different request to the same sequence number. So once a node enters into the prepared phase, now what happens next is it should commit that message, commit that request, as in execute that request. And what it does is it will each node, once it has entered into a prepared phase, means it will send out all commit messages to all the other nodes. So it will send out commit messages to all the other nodes, and the commit message is that say node 2 sends out a commit message to all the other 98 nodes, means what's the significance is it tells the other nodes that it has entered into a prepared phase. Okay, and similarly N100 to N2, all the 100 nodes should be sending out the commit messages once it has entered into a prepared phase, and once all the other nodes have received majority of commit messages. So in the commit phase, node sends out commit messages and once a node receives more than 2/3 commit messages, then I am sure that all the other nodes have also reached a prepared phase. Okay, and I am safe to execute the request R1. And now I can now what happens is once a node have received more than 2/3 of the commit messages, means the node will execute R1 and return to client, return the response to client, and once the client will wait for f+1 responses. Okay, and if all the f+1 responses that are being returned from the node are the same, right, then the client will assume that it was a success, because like see, if nodes are only faulty, this is like a honest node, this extra one node is honest node. Okay, and if one honest node is also telling a result, means then all the other nodes are also in sync and having a consistent view with this one honest node. So based on this logic, it just waits for f+1 replies from all the nodes after the commit phase, and if the result is same, then it logs in onto that result and it displays it to the user. Okay, and so this is the overview of the PBFT algorithm. So it takes place in 3 phases: pre-prepare phase, the prepare phase, and commit phase. And say in between, if some nodes are faulty, right, those are actually less than 2/3 only. So that's why in every case we are having like a majority vote, which is at least 2/3 majority should be achieved. And once it is achieved, uh, the three phases, from one phase to another phase, once the 2/3 majority is achieved, it moves to the other phase, and finally that message is committed and it is executed. So finally, majority of the nodes would either accept the request message, or it will disagree, and it will not um, it will the request won't be accepted. So finally it is having a consistent view. And say suppose the primary node itself is faulty or something, right? Here we mentioned round 1. Currently we are in round 1, okay? And say your primary node itself is faulty, and whatever message it sends out, whatever the client is sending to the primary node is the one which proposes new transactions or new messages, right? If the primary node is still like faulty and is acting maliciously, then the other nodes will get to know of that, because the primary node is sending out conflicting messages. And because of that, what happens is, say like due to some network fault, the primary node is not able to communicate, or the primary node is sending out multiple pre-prepared messages having different sequence number, but the same but like having the same sequence number but different request. It is sending out different pre-prepared messages having the same sequence number but different request, or it's acting maliciously. In that case, you cannot trust the primary node anymore, and you take like a view change. All the nodes will get together, and it will uh, ensure that a view change occurs. A view change means the round number is increased by 1, round plus plus. So in round 2, instead of the node 1 being the primary node, you change the primary node to be node 2. And even if node 2 is faulty, then again a view change occurs and your round number is increased. And node 3 becomes your new leader. So in this way, liveness is ensured, and finally, since like majority of the nodes are honest, right? Finally, you will reach a primary node which is honest, and till then, in that specific round, the primary node would keep on proposing new transactions until some network fault occurs or something, a crash fault occurs or something, and until then, it will keep on proposing transactions. It will be added into your ledger or blockchain network. And once a fault occurs, again a view change will occur. And for this view change also, majority of the nodes should get together and send out messages to increment the round number and elect a new primary leader. Once a node is selected as a primary leader, that is the round number is increased, then that specific round's leader is will be proposing new transactions. So we looked at how PBFT algorithm works, and how safety is ensured by this prepared and commit phase, and how liveness is ensured by changing the view whenever a network fault occurs, or whenever the leader is acting maliciously. Okay, so this is the high level overview of the PBFT algorithm, and the importance of the number of faulty nodes being less than 2/3, sorry, less than a third actually. Over here it's a mistake, it should be less than a third. Okay, so it should be less than a third. Less than a third of the overall nodes is important, because the whole algorithm depends on majority of the nodes replying back with the correct response, right? So any doubts in the PBFT algorithm? Okay, if there are no doubts, then we can end the session. It's already 10 minutes late. Sorry for the uh, extended session. Oh, If there are no doubts, then we can end the session. Okay. And then in that case, let's end the session. Thank you, everyone. See you in the next session. Thank you for making it interactive. See you.